Welcome, aspiring geologists. Today, we're peeling back the surface of our world to look at its very skin, the Earth's crust. It might seem like just the ground beneath our feet, but this thin, rigid layer is where the entire geological drama of our planet unfolds. It's the grand stage where continents collide, oceans are born, and mountains rise from nothing. This is the boundary where the immense forces of the deep Earth finally express themselves, and where we, as geologists, learn to read the planet's epic history, written in stone, mineral, and chemistry. At its heart, the crust isn't one single entity. It's split into two fundamentally different types, each with its own story, its own architecture, and its own chemical signature. First, let's explore the continental crust, the ancient, buoyant, and ever-evolving engine that builds our landmasses. Continental crust is the product of billions of years of cosmic recycling. It forms through repeated cycles of fire, pressure, and collision. Its growth is intimately tied to subduction zones, where water-rich mantle material melts to create silica-rich magmas like andesite and granite. It also grows through continental collisions, which thicken and rework the crust during mountain-building events, known as orogenies. Think of it as a geological sourdough starter, constantly being fed, kneaded, and baked over eons. It has been built, destroyed, and rebuilt for billions of years. Geometrically, continental crust is thick, ranging from 30 to 70 kilometers, with its deepest roots plunging beneath young, high mountain ranges like the Himalayas. Its average density is around 2.7 grams per cubic centimeter. This makes it light and buoyant, allowing it to float high upon the denser mantle below, much like a cork in water. Structurally, it's a complex layer cake. At the top, you have sedimentary rocks, which hold the fossil record. Beneath that lies an upper crust dominated by granite, and deeper still, a lower crust of metamorphic and more mafic rocks like gneiss and granulite. It's not a uniform slab. It's a glorious patchwork of ancient, stable cratons, younger orogenic belts, rift valleys, and vast volcanic provinces. Compositionally, continental crust is dominated by felsic rocks, which are rich in silica and aluminum. We're talking about granite, its volcanic cousin rhyolite, and granodiorite. When these rocks are buried and cooked, they transform into metamorphic rocks like gneiss and schist. The trace elements and isotopes hidden within these rocks are like geological fingerprints, revealing ages that span from brand new volcanic arcs to cratons that are billions of years old. This crust is Earth's memory keeper, a planetary archive preserving the grand narratives of tectonics, climate, life, and the very evolution of our world. Now, let's turn our attention to its counterpart, the oceanic crust. This is the young, dynamic, and fiery sibling, born from the planet's molten heart. Oceanic crust is forged at mid-ocean ridges, those massive undersea volcanic chains that wrap around the globe like a seam. Here, as tectonic plates pull apart, the underlying mantle decompresses and melts, generating basaltic magma. This magma rises, intrudes, and erupts onto the seafloor, continuously creating new crust. It's a conveyor belt system constantly generated, transported across the ocean basin, and ultimately destroyed as it plunges back into the mantle at subduction zones. In terms of geometry, oceanic crust is a stark contrast to the continents. It's incredibly thin, only about 5 to 10 kilometers thick. But it is denser, around 3 grams per cubic centimeter. This higher density is the key to its fate. It's what allows the old, cold oceanic plate to sink beneath a continental plate or another oceanic plate. Its structure is famously consistent, known as the ophiolite sequence. At the top, a thin blanket of marine sediments accumulates over time. Below that, layer 2 consists of basaltic pillow lavas and vertical sheeted dikes that fed them. Deeper still, layer 3 is made of gabbro, the slow-cooled, crystalline equivalent of basalt. Finally, this transitions into the peridotite of the upper mantle. Though geometrically simple, oceanic crust is tectonically powerful. Its density is the primary engine driving the motion of the plates. Its composition is distinctly mafic, rich in iron, magnesium, and calcium, and relatively poor in silica. The star players here are basalt and gabbro. Chemically, it's a direct sample of the upper mantle, offering us a window into the Earth's interior. So, why does this distinction matter so profoundly? Because together, these two types of crust create the entire architecture of plate tectonics. The oceanic crust is the driver. It forms fast, cools, sinks, and recycles itself, pulling the plates along with it. The continental crust is the passenger. It grows slowly, resists subduction due to its buoyancy, and therefore preserves the records of deep time. Their interaction is what controls everything we see on the surface: the creation of mountain ranges, the formation of volcanic arcs, the opening of rift zones and ocean basins, and the concentration of valuable mineral resources. The crust may be a mere sliver of the Earth's total volume, but it is the dynamic interface between the powerful mantle engine below and the world we inhabit above. It is our planet's storyteller, its evolving skin, and the very foundation of every geological journey we undertake. Thank you for joining this exploration. Remember to follow for more deep dives into the world of geology.